Hello and welcome to the very first lecture on RF and microwave engineering. The very first thing to know is that RF stands for radio frequencies, and in the introductory video lecture we saw that the words RF and microwave, even though they mean different things in the strictest sense, these days often they are used rather interchangeably. So compared to the other circuits and systems courses that you may have done or taken so far, the difference between those courses and the RF and microwave course is the fact that you will be working with a totally different set of frequencies. That is to say, you will be working with frequencies which are very, very high. So, as mentioned earlier, the broad range of RF and microwave goes from about 300 megahertz to 300 gigahertz. So, the question is, what is the big deal about this? Even if the frequencies are higher, what difference does it make? Because ultimately a signal is a signal. So it should not ideally matter what the frequency is. The same circuit laws and design and analysis techniques should still apply. Well, theoretically, yes. So the first thing that we're going to see is how these high frequencies pose a rather different set of challenges as compared to low frequencies. Now, in the other circuits courses that you may have done earlier in your academic career, you may also have worked with some of those signals or voltages or currents practically in the lab. So, in your basic circuits courses such as analog or digital circuits, what is the maximum frequency that you have used? In the lab, you will notice that we have signal generators or the signal generators that are commonly used in the basic circuit labs. Their maximum frequency is limited up to maybe 1 megahertz, 2 megahertz, or at the most 10 megahertz. So let us say the maximum frequency that one can use in the basic circuit course is 10 megahertz. So suppose you have a wave or a sinusoidal signal of frequency 10 megahertz, which looks like this. So the time period of that signal will be 1 by f, that is 1 by 10 megahertz, which is 0.1 microsecond. Now the question is, for this same signal, what is the wavelength? As you know, wavelength is nothing but the velocity of the wave divided by the frequency. Now, all waves are electromagnetic waves. For the sake of simplicity, you can assume that the wave is traveling in air. So, the velocity of the wave is 3 into 10 raised to power 8 meters per second divided by the frequency, which is 10 megahertz, which is 10 into 10 raised to power 6. So, how much would that be? That is about 30 meters. Well, so far so good. Now, in your basic circuit courses, how do you practically implement the circuits that you make? You normally use something called a breadboard. A breadboard or a circuit board, it's about this much in length. So the length of the breadboard, let us say, is something which is less than or equal to about 15 centimeters. Whereas the wavelength of your wave itself is 30 meters, which is many orders higher than the length of the breadboard. So this is one observation we can make very quickly. So in the sense, if the frequency is 10 megahertz, I can say that the dimension of my circuit is much small as compared to the wavelength of the wave that is traveling in the circuit. This is the first observation that we can make. This is at 10 megahertz. So therefore, if we reduce the frequency to 1 megahertz or 10 kilohertz, the wavelength of the signal is just going to increase. And it is going to be much bigger as compared to the circuit size. So what this means is that suppose I have a very simple circuit that looks like this. Let us say the length of this circuit is about 5 centimeters. So given this circuit that is working with a single resistor and a capacitor fed by an AC voltage source, at any point of time, obviously the voltage will be sinusoidal. But I can say that between these 2 points, the voltage will be exactly the same. Why? Because the sine wave will be huge as compared to the size of the circuit. So therefore, since this distance is very small as compared to the wavelength of the wave, I can say for all practical purposes that in this region there is negligible change in the voltage. This is the good part about working with low frequency signals. So now let us choose some signal whose frequency lies in the RF region. So let us say we take another frequency that is 30 gigahertz. So in that case, the wavelength will be how much? 3 into 10 raised to power 8 divided by 30 into 10 raised to power 9. So this would make it 10 raised to power minus 2 meters. That's like saying this is about 1 centimeter. Is this correct? Yes, looks to be. Now, 1 centimeter is about this small, or even smaller than this, what I'm showing you. So, if you are working with a breadboard, or you are working with the components that you normally use during your basic circuit courses, the size of one component itself may be as large as a centimeter. So, therefore, what is going to happen is that the wavelength now has become much smaller. The wavelength has now become much smaller than what it was at 10 megahertz. So therefore, now the wavelength of the wave is going to become comparable or no longer negligible when you are comparing with the size of your circuit. Let us see how. So let us say I have a wave source that is connected to a load. I have a source and I have a load. Now, suppose the distance between the source and the load is some length quantity L. And there is a high frequency wave that is flowing. So let us say this much is lambda. The distance between two troughs is lambda. So clearly you can see that lambda and L are comparable to each other. So now what we are seeing is that because of this AC source, the voltage that it generates is anyway a function of time, but we can no longer say that the voltage at the source and the voltage at the load are equal, because now the wavelength and the length of the circuit itself are comparable. Had lambda been much bigger than L, then we could have said that okay, whatever is the voltage across the source, the same is the voltage across the load. So therefore, the voltage is some function not just of time but of length also. That means it is a function of time because it is a sinusoidal signal, but it is a function of the length or the position also, because the wavelength and the length of the circuit are comparable. The wavelength of the wave is comparable to the length of the circuit. So let us say at the source I am seeing a trough, but at the load I may observe some voltage which is not the trough. So likewise, I am observing a trough at the source, I am observing a peak somewhere in the middle of the line. So this is something which is new. This is something which is very interesting to note, that in basic circuit courses, analog as well as digital, we assume that the voltages and currents are functions of time only. But here in RF and microwave, you have this length variable also. Thankfully, our job will become little easier because the time and length factors can be segregated. The time and length factors can be segregated and treated as independent quantities because they really don't depend on each other. The fact that the distance between the source and the load could be as small as possible, could be as large as possible, but its time behavior would not change. The wave would still remain a sinusoidal wave as a function of time. So likewise, we are going to have some kind of a length distribution or the voltage distribution on the line as a function of length once we know what kind of function the voltage is with respect to time. So therefore, we can treat the time and length effects independently, although for a complete clear picture, they must be brought together. So this is the very basic difference between the circuits that you analyze or use in your basic courses versus an RF circuit. So wherever you have such kind of circuits where the length and wavelength become comparable, those are RF and microwave circuits. So we took a very simple example of the connection between a source and a load using a pair of wires. So in this simple connection that involves nothing else but just a pair of wires, but here what was the underlying assumption? The underlying assumption is that the wavelength and the length are comparable. Lambda and L are comparable to each other. So therefore, this pair of conductors is now called as a transmission line. So the word transmission line comes from the context of electrical engineering or power delivery systems, where you may have noticed there are big lines which essentially deliver the power from the electric station to our homes for domestic use. Even there, although the frequency is a lot lesser than RF microwave, but because the distance is so large, it may so happen that the wavelength and the length of those transmission lines may become comparable. So transmission lines is something that I'm sure you have already come across in your basic course on electromagnetic field theory. So a pair of conductors can form a transmission line, just like the pair of conductors which are used here. So let us take a very quick recap of what transmission lines look like. Well, as you know, in transmission lines, the voltage or the current are functions of time as well as length. So what do? For the sake of convenience, we want to use the same theorems that we use in our circuits, that is things like Ohm's law, Kirchhoff's laws. We still somehow want to make them applicable over here. So therefore what we do, in the transmission line, we consider a very small section. So if you assume that this is the positive x direction, this infinitesimally small section that is called as delta x, it's very, very small. So what we can say is that this delta x is much, much small as compared to lambda. So the question now is, how small should this delta x be? How small should this delta x be so as to consider that this distance is indeed sufficiently small? Well, there is no answer for this. Some people say 100, there should be factor of 1 by 100 as compared to the wavelength. Some people say 1 by 1000, and they're right. The smaller it is a factor of lambda, the more solid our assumption will be that indeed delta x is much, much small as compared to the wavelength. But practicing engineers do put a number saying that if delta x is less than lambda by 20, this is considered a safe approach or a safe approximation. For most applications. Now, there is some current which is flowing along this conductor and some current obviously which is returning from the other path. Obviously, there will be some end of the line somewhere, just like this. So the current will flow and come back. But as you know, this is a time varying current. This is a time varying current. So whatever is going over here, the same has to come back. to ensure conservation of energy. Now the question is, what are the electrical quantities I can represent at least inside this delta X section of the transmission line? Well, if I take a magnifying glass and observe only what is inside this delta X section, so I am now going to magnify this and I'm going to observe what is inside. So first thing, there are two wires. So what we will do, just for the sake of simplicity, let us assume that the second wire is a ground. So what we will do, we will simply denote the second wire as ground. Because as you know, it is always easier to work with signals out of which one of the terminal is ground and the other conductor or the other terminal is used to denote the voltage. So effectively, these wires or these conductors are metallic. Now we can make wires out of copper, we can make wires out of silver, whatever it is, there will be some amount of resistance of the wire, that is R. Likewise, between these two wires, what do you have? Between these two wires, there is some medium which is not conducting. There is some medium between these two wires which is not conducting. So there is an insulator over there. Now, suppose there is a current which is flowing through this wire and that is time varying. Now, as you know, there is always a magnetic field that is generated around any current carrying conductor. So since the current is not a DC current, it is a time varying current, even the magnetic field that is generated around the conductor will be time varying in nature. So therefore, what's going to happen? Because of this time varying magnetic field, there will be some EMF that is induced back onto this conductor, and that phenomena is called inductance or the self-inductance of the wire L. So these resistance and the inductance are two quantities which denote the behavior of the wires by themselves. Now coming to what is the medium between these two wires, as I mentioned just a few moments back, it is some kind of an insulator. It could be air, it could be some other material which is an insulator. Now what happens is, an insulator should have very high resistance. So just like for wires, the unwanted behavior is resistance. For an insulator, the unwanted behavior or the unwanted electrical property that it should not exhibit is something called as conductance. That is the reciprocal of resistance. Remember, this G is not 1 by R because this G is of the medium that is between the wires. Finally, we have two currents which are flowing in opposite directions. Obviously, there will be different charge accumulations along the two conductors. So therefore, this will cause some capacitance C. Now, notice one thing. We have only magnified what is inside this small delta X. Now, for the whole length of the conductor, there will be multiple such circuits, RLGC, RLGC, RLGC. So therefore, what we do as a good convention is that we represent these resistances, inductances, conductances and capacitances as per unit length quantities. So therefore, the unit of R is ohm per meter, L is Henry per meter, G is mho per meter, and capacitance is farad per meter. Now, why do we do this? What is the harm in keeping them as ohms, henries, and so on? Well, we are doing so is because we are ourselves introducing the assumption of this delta x, infinitesimally small length of the line. So therefore, it is very, very difficult to actually measure the resistance for that portion of the line by practical means. So therefore, what we do, we measure the resistance of the wire from end to end, and simply we can divide by this quantity L. That will give us what is the per unit length resistance. Same for the other quantities also. So we measure them end to end, and since the nature of the transmission line is uniform, we can quite safely divide those whole quantities by the length of the line, that is L, and get what is the per unit length quantities. So therefore, this resistance is not R, but R multiplied by the actual length over which we are analyzing. So therefore, this is R times delta X. This will be L times delta X. This is G times delta X, and this will be C times delta X. So always remember this. R, L, G, C are taken as per unit length quantities. They are taken as per unit length quantities. So therefore, we always have to multiply with the length in concern so as to get the actual resistance and other values over the section of the line that is under consideration. So this is the first thing that you need to know about transmission lines. Now, let us again take a basic recap of what you have learned in your waves course as far as transmission lines are concerned. What we learn, or what you have learned over there, is that because of the fact that lambda and L are comparable, that is, the wavelength of the wave is comparable to the dimension of the transmission line, effectively the analysis of voltage and current becomes little different from what we expect to see in circuits, or at least the basic circuits. So the analysis sort of involved that you take this length section and the length section of the transmission line, and then apply the KCL and KVL on it, and you will see that essentially as a function of position the voltage would look something like this. So effectively, this is a solution for an ordinary differential equation, and this small gamma, this is the symbol for small gamma, and this is called as the propagation constant. So if you write this in the mathematical form, you can get it in the form of, or using the electrical quantities R, L, G and C, which we mentioned about in the previous page. So it looks something like this. So Omega, as you know, is the angular frequency. That is nothing but 2 pi f. This is what it looks like. Now, irrespective of what gamma is, what you see is essentially that there are two terms. Recall that the first term, which is this decaying exponential, that is e raised to minus gamma x, this indicates a wave traveling towards the plus x direction. And this one indicates a wave traveling towards minus x direction. So effectively, if you solve for the voltage on the transmission line as a function of distance x, you will see that the solution essentially involves two waves. One wave which is going from left to right, the other which is going from right to left. So, meaning we normally think that we are sending the signal or the wave from the source to the load, where the source is essentially on the left and the load is on the right. So there should be one wave, but actually there are two waves. So this is something which is very interesting. Likewise, if you solve for the current, again, what I am saying here should be a recapitulation of what you have learned in your waves courses. And this is a modification of this expression. This term Z0 is called as the characteristic impedance. The characteristic impedance of the transmission line. And by formula, that looks like this. You can do a sanity check yourself and find out that indeed this has the dimensions of impedance. Now, we have defined this quantity Z0. You already know about this quantity Z0 from your previous year's electromagnetics courses. But it is important to define using simple English what Z0 is. If somebody asks you, how do you define Z0? You cannot simply say that Z0 is this quantity by this quantity under root. No, that is not definition. That is just formulating Z0. So the way to define Z0 is very, very simple. Now suppose I have this source and the load connected through a transmission line, and this is the positive x direction, and at some point I have V of x, and over there the current is I of x. Suppose I launch a wave from the source. Obviously it will take some time to reach the load. So the time taken to go from the source to the load, that is small t, is nothing but L divided by the velocity of the wave, where L is this distance. So now suppose the wave starts and is now traveling. It is traveling in such a way that it has not yet reached the load. Then what will be V of x, what will be I of x? So traveling wave from source to load, but not yet reached the end of the line, that is the load. what will be v of x? Well, we will definitely have this term. But will the second term be there? No. Because until and unless the first wave hits the load, there can never be a wave that is traveling backwards. You cannot have a wave that is reflected from the load unless there is some wave that is incident first. So therefore, under such condition that the wave has not yet reached the load, v of x will simply be this. Likewise, current, even it will be the same for the current, only this term will be there. Now, suppose I want to measure what is the impedance seen at any point of the line, that is z of x. That is nothing but v of x by I of x. Simply divide this two, what will you get? You will get z0. So therefore, z0 or the characteristic impedance is defined as that impedance which is seen by a wave traveling along a transmission line but not yet reached the end of the line or not yet reached the load. Z0 is the characteristic impedance, which is nothing but the impedance that is seen by a traveling wave on a transmission line that has not yet reached the end. Now please remember one very important thing. This Z0 is a function of R, L, G and C, which are per unit length properties on the line. So therefore, this Z0 is not a physical impedance. This is an impedance that exists at every point on the line. This is called as a distributed impedance. You cannot simply expect to cut a line at any point and expect to see a resistor over there of value Z0. No, that is not how it is. Z0 is a distributed impedance that exists at every point on the line. But it is not a physical impedance that you can see with your eye, because it is a function of R, L, G and C, which are per unit length characteristics of the transmission line that exists along the line at all points, because there are infinite number of those delta X sections that make up the whole line. So this is how we define what is Z0. So again, suppose we have this source, we have a load, let's call this as ZL, because loads can be real, they can be complex. And let us assume that the line has the characteristic impedance, that is Z0. So far what we took this convention, that if you go to the right, it is positive X. But it so happens that it is the load which governs a very important part of the analysis of transmission lines. So what we are going to do is that we are going to look at the transmission line from the load perspective. So therefore, we are going to say that let us define a quantity called L, which is positive towards the left, and at the load, this quantity L is 0. So therefore, what we can say, just by looking at L and X, we can say that L is equal to minus X. We are simply changing the perspective or changing of reference. So what was earlier V of X will now become V of L, and that is nothing but V plus e raised to gamma L plus V minus e raised to minus gamma L. By the way, V plus and V minus are constants which are obtained as a result of the differential equations. So I of L would also similarly become something like this. So as we discussed earlier, this gamma, which is the propagation constant, the small gamma, that can be represented as a complex number alpha plus j beta, where alpha is called as the attenuation constant Why? Because if you substitute this form, e raised to alpha L will be purely real, and it will denote the way the wave magnitude changes as a function of L. So this is called as attenuation constant, and beta is called as a phase constant. So if the line has some resistance or conductance, then alpha essentially becomes significant. But what do we want? We want that our line should be lossless. That means alpha should be 0. This is called as lossless transmission line. And this is the assumption that we are going to use for most of our work in this course, unless mentioned otherwise. So therefore, if alpha becomes 0, then what will the VL and IL be? So V of L will become V plus times e raised to j beta L plus V minus e raised to minus j beta L. And I of L is equal to V plus by Z0 e raised to j beta L minus V minus by Z0 e raised to minus j beta L. Right? Is this fine? Great. So now these two equations are something that are going to be useful for much of our analysis in the course. Now suppose we have this transmission line and we look at the load. Load means L is equal to 0. So at the load, what happens is we have two waves. Let's call them as forward wave, which looks like this, V plus e raised to j beta L, and the reverse wave, which flows from right to left, that is V minus times e raised to minus j beta L. So over here, if we put L equal to 0, the forward wave will become V plus and the reverse wave will become V minus. So therefore we define something called as reflection coefficient at the load, that is gamma suffix L. Both gamma and L are capital. Please do not confuse this capital gamma with the propagation constant. So that will be equal to reverse wave by forward wave. And that is nothing but V minus by V plus. Right? So in that case, in that case, we can also define something called as reflection coefficient at any point L on the line. So the definition becomes, or the definition stays the same. So the reflection coefficient is defined as the ratio of the reverse wave to the forward wave. So at any point L, effectively we have V minus times e raised to minus j beta L as the backward wave, and V plus e raised to j beta L as the forward wave. So this essentially becomes V minus by V plus times e raised to minus j to beta L. But what is this quantity? This quantity is gamma L, that is the load reflection coefficient. Gamma L times e raised to minus j to beta L. So that is one way to find out the reflection coefficient at any point on the line if you know the reflection coefficient at the load. So now if we go back to the load, if we again go back to the load, so V of L will be what? V plus V minus, and I of L will be V plus by Z0 minus V minus by Z0. So since L is equal to 0, we should say V of 0 and I of 0. Now if I divide V of 0 by I of 0, what is the quantity I will get? This is the voltage across the load divided by the current through the load. So that is nothing but the load impedance itself. So what you will see, this would reduce to V plus V minus divided by, if you take this 1 by Z0 common, this is what it will look like. So if I just do a little bit of manipulation, I can say that this is Z0, this will go on top. Now if I divide both numerator and denominator by V plus, I will see that this is 1 plus V minus by V plus divided by 1 minus V minus by V plus. As we have already defined, this quantity is nothing but the load reflection coefficient gamma L. This is 1 plus gamma L divided by 1 minus gamma L. So if I want to define now gamma L, that is the load reflection coefficient, just by cross multiplying and a little bit more of manipulation, I will get this. This is the load reflection coefficient as a function of load impedance as well as the characteristic impedance of the line. Now, just by looking at this, I can say that the magnitude of gamma L will always be in this range, 0 to 1. This is something which I can say just by looking at this, because in magnitude this ratio can never ever exceed 1 because the numerator will be always smaller or equal to the denominator. So that means if gamma L satisfies this quantity, even the reflection coefficient at any other point of line on the line also will satisfy the same. That is, gamma of L will satisfy this, because as we had defined, gamma as a function of L is nothing but gamma L times e raised to minus j 2 beta L. So if this quantity gamma L follows this inequality, even the left hand side must follow this, because the magnitude of this e raised to minus j 2 beta L can never exceed 1. So this is something we know, that the reflection coefficient in magnitude can never exceed unity. At the most it can be unity, but never beyond that. So mod gamma L can be equal to 1 when? If ZL becomes equal to infinity, in which case this will tend to 1, or ZL tends to 0, in that case this will become 0 and gamma L will become minus 1. Any other condition? Any other condition when gamma L magnitude will become 1? Well, think about it. Now, when will mod gamma L be equal to 0? Easy, it will be equal to 0 when ZL will be equal to Z0. This condition, when the load impedance is equal to the line characteristic impedance, this is called as a matched condition. And this is extremely desirable. Why? Because if the line and the load are matched, that is, if ZL is equal to Z0, there will be no reflection at all. That means whatever is the wave that is traveling from the source to the load will get fully absorbed in the load itself and nothing will come back. So that indicates that there is no loss of energy. The whole power that the wave is carrying, or the whole energy that the wave is carrying from the source to the load, will all get absorbed in the load. So therefore, matched condition is very, very desirable. And a lot of our work in this course, at least for the first half of the course, would have something or the other to do with matching. So now you know that having reflections in a circuit or having reflections in a line is not good from the energy perspective. Also, it is not good from the source perspective. If that's a wave that is coming to the source, it might cause some damage to the source, which is only equipped to generate the waves, not dissipate them. So therefore, whatever be the reason, we always try to ensure that the reflections are kept to a bare minimum. If not 0, if gamma L is not 0, then something very, very small is something we try to ensure. Thank you.